Hello again, everyone. This is Amir McKean, electrical engineer, author, publisher, and founder of AIC Publications and the Black Stimporium podcast, your number one source for science, technology, engineering, and math, how to start your own publishing enterprise, building generational wealth, economic empowerment, all centered around the Black African American experience. Back again with another tutorial in the AIC Publications 10-minute engineering program where we demystify the math and simplify the science. Today, we are going to be talking about resistance, the load. Similar to a traveler on a plane or a car, the traveler will encounter things that have to often be addressed that will slow them down, whether it be changes in weather or a myriad of other undetermined issues. They become loads that must be planned and accounted for. All right. Current is the same. Wherever there exists a current and a voltage, there will always exist a load that current has to account for on the journey to get to that lower voltage. This load is called resistance, and it is the opposition to current flow. Its unit of measurement is the ohm, and that's represented by the Greek letter omega. Now, this is similar to friction resistance, which opposes motion, yet as a byproduct, it generates heat. Resistance is the natural byproduct of electrical energy, and it cannot be ignored. It's the byproduct of this. Now, the amount of opposition to the current flow in any material depends on the amount of free electrons it has, as we talked about before, and how many obstacles the electrons come across while moving through the material. The next image that you're looking at is the symbol that we use when we do schematic design for a resistor when it's drawn on a paper with other circuit symbols. Such a paper or printed representation of the electronic devices, as we said, that's what is called a schematic. Now, when electrons move through a material, they will encounter other atoms of the material that are always bouncing against the material as a result of heat, defects, or impurities in that material. All of these issues play a factor in a material's resistance level. Now, remember from the where does electricity come from lesson that we did earlier, that materials or elements with many electrons in the outer shell don't get rid of electrons easily. And because of this, they are often called insulators. Now, for this reason, insulators have high levels of resistance. Given this information, it stands to reason that the smaller the diameter of the wire of the conductor, the smaller the electron flow. Now, above, what you're looking at here is a list of standard wire sizes according to the American wire gauge. Notice that as the gauge number increases, so too does the resistance. However, as the gauge number increases, the diameter of the conductor decreases. This means that the greater the wire number, the greater the resistance. Or one could say that the larger the wire, the larger the resistance. It is also from this same chart and the periodic table that we learn the following things that can determine the resistance of a material. One, you have the material type. The second, you have the cross-sectional area or the diameter of it. Then you have the length and then the temperature. Now, your material type, as we talked about before, that's going to be determined by the periodic table. The diameter, as we just talked about, if the diameter is small, your resistance is going to increase. If the diameter is big, your resistance is going to increase. And the other two, the length and the temperature, are directly proportional, which means they'll increase the resistance along with the increase in length and the increase in temperature. Now, for now, it is important for us to discuss the bona fide resistor types. These are used in every circuit design imaginable. As I said earlier, resistance is also a load, which means that every object in the circuit will have some resistance, which forces the voltage source to have to carry or deliver enough voltage for each component in the circuit to work. This means that in each branch of a circuit, the total voltage should equal the individual sums of every voltage drop in that branch. For a series circuit, the voltage, the resistance, and the current equations would be simply the total voltage would be equal to voltage 1 over voltage over resistor 1 plus voltage over resistor 2 plus the voltage over resistor 3, and it goes on and on. Your current in a series circuit is going to be the same in every single resistor or component in that series circuit. And your total current would equal the individual current in component 1. It would equal the individual current in current 2, or in component 2, so on and so forth. Now, for a circuit in parallel, the voltage and the current equations would change. More on this a little bit later. But the dedicated resistors placed in a circuit are used for the purpose of controlling the current for the dedicated purposes, or setting a voltage at a particular level, or simply to adjust another circuit behavioral parameter. Now, when you go to this slide that we got to a little prematurely a little bit, we're getting into the types of resistors. Now, these are fixed resistors, and then you also have variable resistors. Two types of resistors, fixed and variable. This means that there are resistors that have permanent amounts of resistance and resistors whose resistance can be increased or it can be decreased. The most basic resistor is the color-coded one that you're looking at right now. The first color to the left represents the value of the first digit of that resistor value. The second color represents the same digit, the second digit of that resistor value. The third color represents the number of zeros that are going to follow in that number designation. The fourth color represents the tolerance in percentage, whether or not it's going to be plus or minus 10%, plus or minus 5% of the resistor value. Now, the resistor in the image that you're looking at has a value of 220 ohms with a tolerance of plus 5% or minus 5%. This means that the resistor value would be measured within a window of 220 multiplied by 0.05, which would give you 11 ohms, and would fall in the window of 220 minus 11, which would mean this resistor would be in the value of either 209 ohms to 231 ohms. Now, there are resistors that have tolerance levels that go to even 1% and smaller when precision is really, really needed. But this 220 ohm resistor is a fixed resistor, and it's fixed at its value. Now, the complete color code that you're looking at, it denotes all of these different resistors, different resistor values, and how we determine the basic resistor values. Other resistors are considered variable, and they usually have a tap at the center where the resistance itself can be adjusted with the simple turn of an adjustable knob. Other variable resistors, they may have a slider in place of the tap that can be turned, and the slider can just be literally slid to the left or to the right, which can be used as the adjusting mechanism for that resistor. Now, if you've enjoyed our content and want more of it, I need you to do 3 things to help us reach more of our audience. First, go to our website using the link that you see on your screen and subscribe to the AIC Publications newsletter. If you do that, you will get weekly emails whenever we release new tutorials, new podcast episodes, new books, contest giveaways, and more. By doing this, you'll also be able to get a free book, and it helps us reach out to our community directly should this platform that that are watching or listening to me on should go away for whatever reason. Second, I need you to like the content on the platform that you're seeing now, because that will help draw other people on this platform to us so that we can get them to sign up to be our subscriber at aicpublications.com. And the last, we want you to share our content with at least 3 of your friends using the hashtag AICpublications and provide a link to our website. Thanks in advance for helping us demystify the math and simplify the science. We want all of our community members to attain the knowledge, innovate for success, and command your future. Till next time, we wish you all nothing but the best. Peace.